Here's another example for a curve sketching section. This is another polynomial, and we'll work through this one, and let's see what we find out. So we're just graphing this. A couple of things to notice. Polynomial, so the domain will be all real numbers. This is an even degree polynomial, so the range is not all real numbers. Could be anything, I guess. I mean, not all real numbers, but could start at any number, really. So first we have the domain, all real numbers. Let's see if we can find the intercepts. So the y-intercept very easily is found to be the origin. And if the origin is y-intercept, the origin is also an x-intercept. That kind of goes hand in hand. Of course, the way we get the y-intercept is plug in 0 for the x's. So 0, 0 is also an x-intercept. The way we get the others, of course, we're going to set this equal to 0 and solve for x, x to the fourth. Let's factor out an x squared. That leaves us with 8 minus x squared. So we get, of course, x equals 0 from the x squared, and then we get x squared equals 8. So x is going to be plus or minus 2 square root 2. And I may need my calculator for this one. Let's see. Sometimes I don't work these out beforehand, and usually that is not a good idea, but we'll see what happens. All right, so x-intercepts, we have 2 square root 2, comma 0, negative 2 square root 2, comma 0, and then, of course, origin. Next, we could talk about asymptotes, but of course, with polynomial, no asymptotes, so none. And then last thing we could talk about, well, not the last thing, but in the first few preliminary things we can easily discover, symmetry. Now, most functions are not symmetric at all, but in this case, we have an even function here, x squared. We have an even function here, x to the fourth. So this function is even, and the fact that it is even tells us it is symmetric about the y-axis. And so that at least, even if we don't really use that while we're sketching the graph, once we get the graph, we can at least use that and see if it fits what we expect. I may or may not really use that. I guess kind of using that with the other things that we need. All right, so what else do we need? We need to take the derivatives. So let's find y prime. So y prime will be 16x minus 4x cubed. Let's set that equal to 0. We can factor out a 4x, and that gives us 4 there minus x squared. So we get x equals 0, and x equals plus or minus 2. So let's see where this is increasing or decreasing. Now, what I think I would do is, I know the shape of this. I know that this is an even degree polynomial, which tells me that the endpoints are going to be going in the same direction. And since this highest degree term is negative, that tells us that the endpoints are going down. So probably it's a degree 4, so probably like something like that. So let's use that to our advantage. So we know that once we get to -2, so we have -2, 0, and 2. So let's put these in order. And you could test these if you want. You could plug in -3, you could plug in -1 and 1 and 3, test these intervals and see. But I'm going to use the fact that I know what shape this graph is in. So we know we're increasing till we get to 2. Then we're going to be decreasing. Then we're going to be increasing, then we're going to be decreasing. So we know we have to be increasing on this end. We know we have to be decreasing on this end. I guess the only question is we might should test these two, maybe. And we could. So if we plug in -1, we get a negative for this term, we get a positive for this term, so that gives a negative. If we plug in a positive 1, that gives us a positive here and a positive there, so that's going to be positive. So turns out we were right. So you can at least get some of this for sure based on what you know this graph looks like. The turning points in the middle, those are not as easy to see just right off the bat. So with a degree 4 polynomial, there can be at most 3 turning points. So it's going to change direction at most 3 times. It has to be twice, or it has to be once or 3 times. It cannot be twice, actually, because you go in the same direction. So it can either be change direction 1, 2, 3 times, or it could just be once if the graph maybe looks like this. So it is possible to have a degree 4 polynomial that looks like that. But we know for sure it's one of these two going in, and it turns out that it's going to be this one. So what else do we need? We need the second derivative. So that is going to be 16 minus 12x squared. Let's set that equal to 0. We can factor out a 4, and we get 4 minus 3x squared. Set the equal to 0. We get 3x squared equals 4. X squared equals 4/3, and then x is plus or minus 2 over square root 3. All right. Now, we kind of know, based on the fact that we know that this graph looks like this, that we have an inflection point here and we have an inflection point here. So, and we know just based on this that that's going to be these 2 points. So let's draw our little chart. And so we have our intervals here. So we have our interval -infinity to -2. We have our interval -2 to -2 over square root 3. Then we have -2 square root 3 to 0, 0 to 2 square over square root 3, 2 over square root 3 to 2. And let's see if I can move this. I don't know if I can move this in. Maybe I can. Yeah, I guess I can. We'll just run off the page a little bit. That's okay. 2 to infinity. So, and we kind of should know basically what this is going to look like. So these are intervals. They're not ordered pairs. So, we have our f prime or y prime. Let's use y prime. That's what we've been using. Y prime, y double prime, and then we'll talk about the shape. Although we kind of already know this, but still good practice. If you can always do it this way. The polynomial in this case is a little bit exceptional because we kind of already know what the shape is. So let's look back over here. So the first derivative, I guess we do probably need to do the second derivative with these before we get too far into that. And you can test these if you want, but we know that it's concave down, and then it's going to be concave up in the middle, and then concave down. So negative, positive, negative. But if you want to test the intervals, you can. So up until -2, first derivative is positive. Then it's going to be negative until we get to 0. Then it's going to be positive to +2. And then it's going to be negative after that. Second derivative is negative until we get to -2 over square root 3. Positive between -2 over square root 3 and +2 over square root 3, and then negative after that. So now what is the shape? So increasing concave down looks like that. Decreasing concave up, that cannot be right. Decreasing and concave up. Decreasing, that should be decreasing. Yeah, that's decreasing and concave down. Decreasing, concave down. Now, how did I know that? Because these have to be smooth curves, so you can't really draw increasing concave up and then decreasing concave. That's not smooth. We know this is a smooth curve. That's not smooth. So that's how I knew that one of these was wrong. So that was just my mistake. Going negative infinity out to negative 2 square root 3 is negative in both of these sections. So all the way from here to here is going to be negative. So decreasing concave down. All right, now decreasing concave up, that looks like that. Increasing concave up looks like that. Increasing concave down looks like that. And decreasing concave down looks like that. All right, so now let's plot our points. And it's probably where I need my calculator. So let's find the y value for each of these x values. So y of negative 2 is 8 times 2 squared minus 2 to the 4th, 16. And negative 2 over square root 3 is 9.33 repeating. Y of negative 2 square root over square root 3, 9.33. Y of 0 is 0. And then, of course, since this is even, y of 2 will also be 16. Y of 2 over square root 3 is also 9.33. So you could put that in the calculator, but this is an even function, so that is going to be true. And then y of 2 is 16. So now we can plot these points. So negative 2, 16. Negative 2 square root 3, that's a little bit more than 1. That's going to be 9. We're just kind of doing this approximately. 0, 0. And then, of course, you have the symmetry. And so we are, until we get to negative 2, until we get to this point, we are increasing in concave down. So it's going to look like that. Then we follow this shape. Then we follow this shape. Then we follow that shape. Then we follow this shape. And then we follow this shape. Like that. And 2 x-intercepts, 2 negative 2 square root 2. That'd be negative 2, negative 1, 1, 2. And then this x-intercept would be 2 square root 2. Don't care if it's not actually proportional. It doesn't really matter. Mathematicians label things however they want it to actually be, not how they want it to look. All right, so that's how we do that. Probably said this in the other videos. I'm doing this one much later than the other ones that are in this section. So I don't remember everything I said, but get a process. It doesn't really matter the order that you do these. So finding the domain first is not absolutely necessarily the first thing. You could, as long as you do it. So find the domain, find the intercepts, find the asymptotes if there are any. Check out the symmetry. That will help. Just so this is symmetric. And then first derivative, get where it's increasing or decreasing. Second derivative, find the concavity. I mentioned intercepts. And then set up this chart. Chart is great. I think this is the best thing that you could do. And then just connect the dots. Did that as a kid. You can connect the dots. So there you go.